how do you actually see the invisible? How do you perfect the design of a jet wing before a single piece of metal has even been cut? Well, today, we're diving into the incredible technology that makes it all possible. Computational Fluid Dynamics, or as most people call it, CFD.
I mean, just stop and think about that for a second. How do you predict what's going to happen inside a combustion chamber that's hotter than the surface of the sun without building and, potentially blowing up millions of dollars worth of hardware?
Or how about this one? How do you find those precious milliseconds of lap time by figuring out exactly how air will flow over a car that, right now, only exists as a file on a computer? The answer to all of these questions is a technology that lets us visualize and predict the invisible. And that's where CFD comes in. The best way to think about it is as a digital laboratory, a virtual wind tunnel. Instead of building a physical model, you build a digital one, and you let a supercomputer simulate the unbelievably complex dance of fluids, whether it's air, water, or anything else, as they interact with that object.
Okay, so how on earth does this digital magic trick actually work? I mean, how do you take something as real and physical as an airplane and translate it into a language that a computer can understand? Well, the very first step is to turn that physical reality into a digital grid. You see, here's the fundamental problem. The flow of air over a wing is, for all practical purposes, infinitely complex. And computers, well, they just can't solve an infinite problem. So the core idea behind CFD is as simple as it is brilliant. You break down that enormous, continuous space into millions of tiny, finite, manageable pieces that a computer can actually solve. We call this digital framework a grid, or sometimes a mesh. You can think of it like the digital skeleton of the object and all the space around it. This whole process is called discretization, and each tiny cell in that grid becomes its own little miniature arena, a control volume, where the computer is going to solve the fundamental laws of physics.
But, of course, not all grids are created equal. On the one hand, you have structured grids. They're neat, they're orderly, just like a checkerboard. Super efficient for a computer to work with, but they really struggle with complex curves. On the other hand, for something really tricky like the front wing of an F1 car, you need an unstructured grid. This thing is more like a flexible web of triangles that can wrap perfectly around any complex shape, capturing every single nook and cranny.
All right, so we've got our grid. We've got our digital map made of millions of tiny cells. Now what? Well, now comes the fun part. We tell the computer the rules of the game, and the rules are the fundamental laws of physics.
These are the absolute, non-negotiable laws of the universe for fluids. You can't just create or destroy mass or energy out of thin air, and the real star of the show here is the conservation of momentum, which is governed by the famously, notoriously complex Navier-Stokes equations. These equations are basically the mathematical blueprint for how every fluid behaves. Now, the most common way to apply these laws is something called the finite volume method. And honestly, the best way to think about it is like a super strict accountant for physics. For every single one of those tiny cells, it makes sure that what goes in must come out. Mass, momentum, energy, it's all perfectly tracked and balanced from one cell to the next across the whole simulation. It has to add up.
And this is where the real magic happens. This whole process takes the beautiful but unbelievably difficult math of the Navier-Stokes equations and translates it into millions of much simpler algebra problems, one for each cell. Now, they're all interconnected, of course, forming this giant digital puzzle. But even though it's massive, it's a puzzle a computer can actually sit down and solve piece by piece.
But even with this incredibly powerful system, reality always has a few more curveballs to throw at us. And the biggest one is a phenomenon that is beautiful, chaotic, and an absolute nightmare to simulate. This brings us to the world of modeling chaos and complexity. I'm talking about turbulence. It's the smoke swirling up from a candle, the chaotic wake behind a speedboat. It is made of swirling eddies and vortices across a huge range of sizes, from massive swirls you can see down to microscopic ones. Trying to directly calculate every single one of those swirls for something like an entire airplane, it would require more computing power than currently exists on the entire planet. It's just not possible.
So we have to get clever. We have to approximate. And this leads to a critical trade-off between detail and cost. At one end of the spectrum, you've got RANS. It's the fastest approach because it doesn't try to simulate the swirls, it just calculates their average effect. It's the workhorse of the industry. In the middle, there's LES, which is a compromise. It simulates the big, important eddies and just models the tiny ones. And then at the far end, you have DNS. This is the holy grail. It simulates everything, but it is so incredibly slow and expensive that it's almost exclusively used for pure academic research.
And hey, turbulence isn't the only chaos we have to deal with. trying to simulate the fiery chemical reactions inside a rocket engine, or predict how millions of tiny fuel droplets are going to behave in a spray. All of these things require their own clever models and approximations to make the unsolvable solvable.
So all of this, the grids, the physics, the models, it gives us this incredibly powerful predictive tool. It almost sounds like a crystal ball, right? Well, not so fast. With all this power comes the absolute need for a serious reality check. There's a famous quote from one of the foundational textbooks on CFD that really says it all. A simulation is not the absolute truth. It's a hugely powerful tool that works with real-world experiments. It doesn't replace them.
And that's because every single simulation is an approximation. It's not perfect reality. That means there are always going to be sources of error. You have modeling errors, because our turbulence models are simplifications. You have discretization errors, because our grid cells aren't infinitely small. And you have input uncertainty, because maybe we just don't know the exact conditions of the real world we're trying to simulate. And all of this leads to the single most important rule in the world of CFD. A beautiful, colorful simulation plot is completely meaningless until its predictions have been checked and validated against real experimental data from a wind tunnel or a physical test. That's how we build trust. That's how we know the results are accurate.
So from perfecting a rocket engine before it's ever fired to designing championship-winning race cars in a virtual world, CFD gives us this incredible window into the invisible world of fluids. We've created a digital laboratory to tackle some of our toughest engineering challenges. So the only real question left is, what problem should we point it at next?